Now we're going to move on to the vascular side of the cardiovascular system. We're going to talk about a couple things in this section, including hemodynamics, arteries, and arterioles. Hemodynamics just being really how's blood flow. I'm going to start off with that. And so one of the principal things that we're interested in when we talk about how blood's moving through blood vessels is the flow rate, or how quickly is that moving. We're also interested in the pressure by which it's moving, but we'll come back and talk about that in just a few minutes. And there is an equation that essentially sets up how this operates. So the flow rate is going to be equal to the change in pressure, which is the delta P, and that's the change in pressure from the beginning to the end of the vessel. So really what we're looking at, if this is a blood vessel up here, we're looking at the pressure, so pressure 1, that is right here as blood goes in, and that subtracted from pressure 2 as the blood comes out of that vessel. So what is that change in pressure from the beginning to the end? And that's divided by the resistance of that vessel. So we can increase rate by doing two different things. We can increase this pressure gradient, so therefore increase the pressure at the beginning of this, or decrease the pressure at the end of this vessel, or we can lower the resistance of this vessel, and both of those can increase the flow rate of blood through that vessel. Now, the changes in pressure are essentially generated by the heart. The heart is going to generate a positive pressure at the beginning of this system, while it's not necessarily changing the pressure at the end, and so we get this pressure gradient that's created by the heart and causes flow to begin in the first place, which is kind of intuitive. The heart is pumping to push blood through the heart. And then the resistance portion of this is actually provided by the blood vessels, and that's actually laid out in this equation right here, R being the resistance, N, this kind of N-shaped value. I don't remember the Greek name for it offhand, but this term right here that we're not going to come back and talk about much after this is viscosity. L here is the length. T in there, length. And then divide by pi times R, which is the radius of the vessel, to the fourth power. So resistance is 8 times the viscosity times the length of the vessel, or the viscosity of the blood times the length of the vessel, all divided by pi times the radius of the vessel to the fourth power. So there's one thing that I want you to notice here is this fourth power right over here, over the radius. And what that means is that the dominant factor in resistance is really the vessel diameter. So we can change the vessel diameter very quickly, change the resistance very quickly by changing the vessel diameter. So just to give you an example, if we double the vessel diameter, this is actually going to equal an 16-fold, because 2 to the fourth is 16, a 16-fold increase in flow. And if we half it, or half the diameter, that's going to result in 1/16 the flow. So by changing this diameter, we're changing the flow rate, because we're changing the resistance, very, very quickly. Okay. So let's look at why do we need to control the cardiovascular system in the first place? And the parameters specifically that the cardiovascular system is trying to keep in tight regulation are two different things, principally. It needs to maintain appropriate oxygen transport. Primarily, this is appropriate oxygen transport to the brain. That's the most sensitive organ that we're going to be talking about. And so really, the cardiovascular system needs to maintain this appropriate oxygen transport. Your muscles, your stomach, your digestive system, a lot of the other systems that you have can go without oxygen for a little while and be okay. But your brain is really sensitive to this. And so really the cardiovascular system is going to do a lot of its changes or its control based on, are we getting sufficient oxygen to the brain? And then the second thing that takes a back seat to that, but then also trumps essentially everything else, is that appropriate pressure. Are we getting appropriate pressure, again, principally to the brain? And here to the brain. So we're going to adjust all of these different factors to try to control that. So we'll come back to that in a little bit, but right now let's talk about, come back away from hemodynamics for a second, talk about arteries. So arteries, these are the initial vessels that are traveling away from the heart. So the functions of arteries is to carry blood rapidly to tissues. These are very essentially large diameter pipes that we can push blood through very quickly, and so we're rapidly trying to take our blood from the heart to whatever tissue that we're trying to get it to. So that's the primary function, but it also acts as a pressure reservoir. So let's talk about what that means to be a pressure reservoir. First off, before we talk about that, we need to talk a little bit about the anatomy of an artery so that you understand how this works. And really, arteries are these very thick-walled vessels. We have the endothelium in the center, and then we have several different layers, including a smooth muscle layer outside that. But the two that I really want you to pay attention to is we have these two elastic layers. They're essentially made up of a lot of different, or not a lot of different, but a large degree of elastin proteins that give this essentially stretchy and rebounding sort of characteristic to them. So we have one internal to the smooth muscle, and we have this other elastic layer that is external to the smooth muscle. So what that means is that we can actually stretch arteries out, and they will rebound to their original conformation. So this is important when we talk about them as pressure reservoirs. During systole of the heart, arteries are going to expand in diameter because we're increasing the pressure in these arteries. They expand in diameter. However, during diastole, so as the heart is relaxed now and it's not pushing out with pressure anymore, these arteries are going to rebound. So they're going to return to their original diameter, and this is going to propel blood. So it's essentially acting as a second pump that is operating as the heart is relaxed. And what this is going to do is it's going to help make the blood flow continuous. So blood flow coming out of the heart is pulsatile in that we're pushing, stopping, pushing, stopping, pushing, stopping. Well, during the stopping phase, the arteries continue to push this blood through, and that's going to cause this to become more continuous. Now, this isn't the only thing that causes the blood flow to become more continuous, but it's one of the major things. And so by the time we get down to the level of capillaries, essentially blood flow is continuous. It's not pulsatile at all. It's going in a continuous fashion. Okay, so that's what I wanted to say about arteries. Let's move on to arterioles, which are smaller vessels that branch off from arteries once we get down to the point where we're in the tissues that we want to deliver this blood to. So let's talk a little bit about the functions of these. First off, arterioles can control the distribution of blood through the body. And so we can change where blood is going based on arterioles, or how the arterioles are functioning. And then also we can control the overall arterial pressure of the entire body with arterioles as well. So how in the world do we do that? Well, that's because these are major resistance vessels. So most of the resistance of the vascular system occurs here in the arterioles. And this is actually another thing that's going to help convert that pulsatile flow into continuous flow, because we have this resistance from that continuous pulsatile pushing from the heart, which has been dampened out by the arteries, but then this resistance offered by the arterioles further converts that to a continuous flow. And the resistance of these arterioles is variable. It's not static. It's not just one value. And so the reason for this is that we have smooth muscle that is surrounding these arterioles that can contract or relax and change the diameter of these arterioles to change the resistance. And so if we have narrowing of these arterioles, we call that vasoconstriction. And if we have enlarging of the diameter of these arterioles, we call that vasodilation. So here's an electron micrograph of these smooth muscle cells that are kind of wrapped around these arterioles, and as these contract, we're going to get increased resistance, vasoconstriction. As they relax, we're going to get vasodilation, which is going to lead to decreased resistance. Okay, but it actually turns out that these smooth muscles are generally contracted all the time in this consistent state of partial contraction. This is known as the vascular tone. Now, this is occurring for a couple different reasons. First off, some of this is occurring right in the smooth muscle itself. Just like the pacemaker cells in single unit smooth muscle, there are some myogenic depolarizations that are happening inside these smooth muscle cells. And so we get some myogenic contraction, or some of the stimulus that's generated within the smooth muscle itself. However, there's also some low-level input of sympathetic input from the sympathetic nervous system that creates this tonal level of stimulation, which also causes a small level of contraction as well. So it's a sympathetic tone. Now, the reason that this is important is that if you need to cause dilation, if you're completely relaxed, you could not cause any more vasodilation to happen. You would be completely dilated. You could only cause vasoconstriction. But because we're partially contracted at all times with these, or most times, with these smooth muscles around the arterioles, if we need to dilate and reduce the resistance of these vessels at any given time, we can do that because they're already partly contracted. Okay, so let's talk about different ways that we can control the arterial rays via the smooth muscles. There's different factors that are going to play into that. They're going to cause this. And the local ones are called intrinsic factors. Okay, so some of these are going to be metabolic changes. We're going to get relaxation, or vasodilation, relaxation of these smooth muscles with several metabolic changes. If we have decreased oxygen, increased carbon dioxide, decreased pH, increased calcium, or excuse me, not calcium, potassium, increased osmolarity, or increased adenosine. Any of these factors are going to tend to cause relaxation of the smooth muscle and cause vasodilation. And the opposite will cause vasoconstriction. Okay, let me just sum these up, though, is all of these are related to high metabolic rate. So, if you think about this for a second, this makes sense. Is if we, for instance, we have these arterioles leading into muscles that are working, all of this is going to happen. We're going to cause decreased oxygen because the muscles are using it. We're going to cause increased CO2 because the muscles are giving it up. The decreased pH is going to be due to lactic acid buildup that is due to the anaerobic metabolism that we could be going through. We can also have increased calcium as calcium is moving out of muscle cells during action potential. So if we have an increase in that, excuse me, I keep saying calcium, I meant potassium. As we have an increase in potassium outside the muscle cells because this calcium is moving, say it again, this increased potassium, is moving outside the muscle cells during increased contraction. We're also getting increased osmolarity because we're taking up water and we're also dumping a lot of things into the muscle, but we also have this buildup of adenosine during high metabolic rates as well. All of this is going to tend to increase these factors, and when this happens, you want increased blood flow to those areas because you need more oxygen. You need to carry away these waste products, and you need to be delivering more nutrients and more oxygen to that area to maintain this higher metabolic rate. And so this will directly affect blood flow to those areas. You don't need to have some signal sent from the brain to increase the blood flow. These local changes can cause it as well. Well, it's not just metabolic changes. We also can have histamine, which will cause relaxation of the smooth muscle around the arterioles and therefore vasodilation. This is related generally to inflammation, and with immune system responses, we're not going to talk too often much about that. But we can also have heat that will cause vasodilation. This will help relieve heat or dump off heat from a certain area, or pick up the heat and move it somewhere else. So heat will tend to cause vasodilation, and cold will tend to cause vasoconstriction. because you don't want to be getting rid of your heat in cold situations. This will tend to cause vasoconstriction, especially in arterioles that are close to the surface of the skin. But really, most of these signals aren't acting directly on the smooth muscle. What's happening is they're going to actually act on endothelial cells that are associated with the smooth muscle. Those endothelial cells will then release some sort of signal that will then act on the smooth muscle. And some of these signals can be these particular paracrine signals, endothelium, prostaglandins, and then an interesting one, nitric oxide, which is actually a dissolved gas, which is an interesting messenger. So generally what's happening is these factors I just talked about are not acting directly on the smooth muscle. They're acting on the endothelial cells of the vessel, which will then relay the signal to the smooth muscle via these signal molecules here. We also have extrinsic control of the arterial radius as well, and this is generally when we want to not control a local sort of response, but we want a global response, a global sort of shift. And this is happening via the autonomic nervous system. So the sympathetic nervous system will innervate arterioles, and there are alpha-1 receptors in the smooth muscle of the arterioles. And when you get sympathetic input and reception by these receptors, is going to tend to cause vasoconstriction by alpha-1 receptors. And this happens in most tissues. These alpha-1 receptors are going to respond to norepinephrine and epinephrine. So as we have those dumped into the body, either from the adrenal gland or from directly from autonomic or sympathetic neurons, we will tend to get vasoconstriction. However, there's some arterioles that have beta-2 receptors instead of the alpha-1 receptors. Instead of causing vasoconstriction, when these are stimulated, they will cause the exact opposite. These are going to cause vasodilation. And this is going to predominantly be in the muscle, skeletal muscle, and in the brain. And they're going to respond primarily to epinephrine from the adrenal glands. Now, think about this for a second. This kind of makes sense. During high levels of sympathetic stimulation, you want to prepare your body for high activity to run away from a bear, something else like that. And so you want to increase the blood pressure throughout the body. And you're going to do that by increasing the resistance. So you need to increase vasoconstriction in most of the body. However, you want that's also going to decrease blood flow. You want increased blood flow in places that are going to need it, particularly places like skeletal muscle and in your brain. And so we need to cause vasodilation, the exact opposite, in those places to increase blood flow to those tissues that are going to need to be active and have a high metabolic rate in response to whatever it is that's freaking you out that you might need to run away from. On the other hand, the parasympathetic nervous system also influences this, but not really, actually. So the parasympathetic doesn't really influence vascular tone at all. It'll influence other things that will lead into changes in the vascular system, but not specifically in vascular tone.